So Sangchul asked me to come and talk to you a little bit about some virtual reality topics. So what I'm going to do is cover a little bit about the human senses and how we can incorporate feeding different stimuli to the different human senses into the designs that we do. Okay, and ways to evaluate different combinations of things. First, I'm going to talk a little bit about virtual reality technology, and mainly around visual types of things that we use in VR. Hopefully, this will lead to lots of questions. So ask me questions and things like that, and will kind of force you to think about designing beyond traditional things. So often in human-computer interaction, people focus on the keyboard and the mouse, sitting at a desk, and then screens and things like that. And mobile devices have changed that a lot, so people don't go to their computers as much as they used to. They're moving around a lot. They're interacting with other people in different ways. And all of that has led to a shift in human-computer interaction studies, so research and design. Similarly, every new technology that comes out, people try and reach back to things that they know from the technology from the past, like the really near past, like 20 minutes ago, and figure out how they can apply what they know going forward. So VR is relatively new to a lot of you, so I wanted to talk a little bit about that and what kind of how the study of virtual reality and how the evaluation of systems in virtual reality happens. So it's a lot of text on the slide, but a couple definitions of virtual reality. So a virtual environment is an environment created by the interaction of a human participant with a world that's displayed by the computer. The displays, is usually multiple, provide information in the visual, auditory, kinesthetic, so that's kind of the haptic or touch area, modalities. Plus now there's smell and taste and things that have been introduced. So this is from 1993, so this is a long time ago. An immersive virtual environment, sensory input to the human from the external world, is ideally wholly provided by the computer-generated displays. Okay, so immersive means that what it does is it cuts out the real world. So we replace the real world with the virtual world. So immersive, there's a couple terms that come up. Immersive, immersion as a measure, presence, like how much do I feel like I'm actually in the environment. Situation awareness is another thing that you hear. Telepresence, these are terms that come up a lot and are the research community uses in different ways, and different communities use them in different ways. And so a lot of the work in the early 90s was, or in the 90s, was to try and figure out what are we talking about? How do we get these terms right so we can actually compare notes on what we're doing? Another definition from 1992, a virtual reality is defined as a real or simulated environment in which the perceiver experiences telepresence. So telepresence, what do you think telepresence means? So if we break this word down, what does presence mean? It doesn't mean gifts at the holidays or anything, but what's presence?
Being somewhere.
Good, so being somewhere. I am present. Present, yep, okay, so I'm here. So what does telepresence mean? So what does tele mean? This prefix in English, what does that mean? What is a telephone?
Like a way to transfer something.
Okay, television. Right? So tele means across. Okay? So tele means, telephone is sending audio signals across something, so across from one place to another. Television is sending visuals, right? So telepresence means that we are somehow, or I am present in a place that's far away from me, or in a different place. Or you and I are both, on the phone with each other, but we feel like we're together. So telepresence doesn't have to be around virtual reality, but it allows us to think, even Skype, right? Oh, look, I really feel like we're together, or FaceTiming with someone as you're on a nice hike somewhere, which you should never do. These make us feel like the other person is with us or we're with them or something like that. So this notion of telepresence is actually really important and underpins a lot of virtual reality. Okay? And we'll talk more about these things. Other definitions or other ways of thinking about this is we think about, so we like to, let me get rid of my, I can update my, my USB-C port adapter. I don't think I'm going to do that. We can think about these immersive systems as combining some level of immersion, so kind of, so what does immersion mean? Like, forget technology, but what does immersion mean? Does anybody know? If you immerse in something, what do?
You're like contained by an environment.
Okay. So if I jump into a swimming pool, I'm immersed in the water. If I'm completely under the water, I'm completely immersed in the water. Okay? So immersion means to surround you. I'm surrounded by something. I'm encased by it. I'm totally immersed. Language is often you hear language immersion. Oh, I'm going to go to live in the French house on campus because I'll be immersed in French. So this is used a lot in languages. Say, if you want to learn a language, go take a French immersion program. They never speak any English. It's always in French, right? So you're completely like, I can't understand anything. That's fine because over time you start to figure stuff out. So when someone goes like this, so in German they might say Stift, 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 Stift. Well, you kind of realize, oh, Stift must be pen, right? So this notion of immersion helps in some way. So some level of immersion, we can think about it in technology if we immerse ourselves, right? We put on a headset or we put on a suit of some kind. We put some gloves on. We're literally immersing our senses in something, okay? Interaction means that it's not just that I'm sitting there and things are happening to me like a movie or something like that, but I can actually do stuff. I can pick stuff up, or I can communicate with you. We can make eye contact. I can hand things to you. Whatever it is that the environment is set up to do, there's some level of interaction. And interaction could be I can just look around, like in some systems, and even that can be like, wow, this is incredible. But after a while, you want to do stuff. So interaction becomes really important. Because in the real world, I can walk over and do anything with anything. I can pick something up, I can write on the board. In VR, in any sort of system, all of that has to be provided. None of this comes for free. So if you want to allow somebody to write on the whiteboard, you have to actually provide some software that allows them to pick up a pen and go do that, right? It doesn't come for free. The nice thing about the real world is everything happens really cheaply. Like this is amazing. It's amazing. Look at that physics. Perfect physics, no latency. Everything works just like you'd expect. And VR, all of that stuff has to be programmed. So there's a lot of math behind it. Or if it's interacting with people, there's a lot of maybe AI behind how the people behave, or capturing that. And interestingly, back then, this circle is a little bit strange to have here. So why is imagination important for these systems? You guys, does anybody play video games like 3D, run around, and sometimes shooting video games or racing games? Or does anybody play these games? It's okay. I mean, I play them, and it's perfectly fine to play these games. So do you feel immersed? You have this feeling of being a little bit? Yeah. Okay. And is it interactive? Yes. Okay. So what is this? Where does the imagination come in? Why is imagination important?
In some way you tell to yourself that the reality that you're experiencing is real. Okay.
Okay. So I think this one you can kind of understand, right? I'm surrounded, I feel. This one you can say, yeah, I understand. This one's a little bit weird because it's like, if I provide you, like in this environment right now, are you using your imagination? Like right here, listening to me talk. Okay. Okay, so let's see. So if I say dog, okay, when I said that, each of you somehow, well, if you heard me, it triggered a bunch of stuff in your head. So tell me about your dog. A dog. What is a dog? White dog, okay, it's white? How big is it? Small one, like, like this small?
Yep.
Okay, so about this tall, yeah?
Maybe just 3 legs.
3 legs, okay. So a small, white, 3-legged dog. What about you?
I thought of a Labrador.
Okay, Labrador. What's a Labrador? What does it look like?
Huge.
Okay,
And very playful.
okay. Any color?
Brown, light brown.
Okay, so brown Labrador, that's about it, this big dog, right? Okay, what about you?
Me?
Yeah,
I thought of a greyhound.
a greyhound, okay.
A retired.
What does a greyhound look like? A retired greyhound.
Tall, skinny.
Okay, kind of sleek, built for speed. Okay, what about you? What?
Make me remember my pet dog.
Okay, so I said one word to you, and it triggered all this stuff, right? So the thing that's really forgotten a lot in these design of these systems is that everybody brings something with them, okay? Everybody has a different backstory. They bring, their feeling of what happened to them this morning. They could be hungry. They bring some rich past that they've had. They bring the people that they know, the places they've traveled to. So everybody brings actually their own stuff. Have you ever read a book and then gone and seen the movie about the book? How is it? What's that experience like?
Sometimes it's exactly how you imagined it to be, sometimes it's different.
Okay.
Generally, the book has more, I don't know, it's just a better experience than the
Yeah,
movie.
it is.
Okay.
Less
How come? How can it be better?
Because you use more imagination. I think once you're reading the book, basically in psychology there is a branch called Gestalt. That explains that we are always trying to fill in some way all the empty spaces. So even if you draw a kind of triangle,
Like this?
it's like that one. Actually that's a good example because versus probably a little kid won't be able to do the associations, but with our experience we know that that's a triangle. So
Yeah, for some people this looks like 3 Pac-Men kind of attacking each other, right?
For some reason we always have to fill those empty spaces.
Okay. Okay.
That's our nature.
So for me, kind of 2 good examples are, so I read the Lord of the Rings books. I made myself read them before going to the movie. And I went in, and that's not Gandalf. I mean, I saw the movie, and I love the movies. They're really good, but it's just not Gandalf. That's not the Gandalf that I imagined and lived with through very thick books, right? The movies are great, and I really love them a lot. And actually, that's probably become my Gandalf now. The other one is there's in the 80s, 90s, there's a movie called Alien. I don't know if you know Alien. So Alien is a horror movie that takes place in space. And there's this bad creature running around that, right, you're trapped in a spaceship. And then slowly all of the crew members are being picked off one by one. And the thing about this movie, it's really, really, really scary. And you never get to see the monster. You see flashes, you hear screams, you see goop falling from the ceiling where they've killed somebody, whatever. But you are so scared of this monster, even though it's not till the very end of the film that you actually get to see anything. And the reason is it's really tapping into everybody's imagination. Okay? It's very, very beautifully done. I won't spoil it anymore, but if you get to see this movie Alien, it's really, really good. The direction, acting is really good. The first one, they made like 7 or something like that. So anyway, this is really important to understand that a lot of times in interactive systems, we strive for realism. We want to make it as visually real, as the audio should be great. Everything needs to be perfect. It needs to represent exactly the way we do things in the real world. That's a really hard problem, technically, getting everything perfect. So this allows us to think about maybe pulling back a little bit and just giving people the essence of what you want them to experience and let them fill in the rest with their imagination. Okay? So that's, again, this is one person's representation of things to think about. And it's pretty old, but this has driven a lot of what we've done in virtual reality. So the components, if we break down some of these definitions, so we have this computer-generated environment. It's three-dimensional, so we can move around in it. It's interactive. It gives us real-time feedback. So we do something, and we get some reaction. And so we throw something, and something breaks or whatever. And it develops this sense of presence. So presence, immersion we can think of as, again, this is not such a cut and dried thing, but immersion we can think of as, if I jump into a pool, I am physically immersed. There's no subjectivity about it. I'm surrounded by the water, okay? So we could think of immersion in virtual reality research as, if I physically cover the person in stuff, like I cover their field of view, so it's not just that they're looking at a screen and they can actually see the real world around here. If I completely surround them, or I put them in a big cave or something that surrounds them completely, they are physically immersed. They're surrounded by whatever it is I'm feeding them. Presence is a state of mind. So we can think of immersion. I want to immerse somebody in a system far enough so that they start to feel present. So this is a cognitive thing. This is a feeling that, wow, I really feel like I'm in the world, okay? And I could physically immerse somebody, but give them really bad graphics, and they won't achieve presence. They won't feel like, oh, I don't, boy, look at that 8-bit stuff going on. That's not really great. Or, well, it's so laggy. I move my head, and everything takes like some time. That's not going to give you, even though they're immersed, they're not feeling present, okay? So a lot of the research that's done in VR is to try and to get to this notion of presence. How do we measure presence? How do we go about that? And we can think about mixed reality. So VR, we talk a lot about VR in this lab. And here's the real world, here's the virtual world. This is a very famous paper called the Reality-Virtuality Continuum by Paul Milgram and Continuu. And this kind of says, so augmented reality, some of you have used or seen, and you will see more of, and this really has to do with merging the real world and the virtual world. You've also heard of virtual reality, and of course you've heard of the real world. It's a fun place to visit. There's also augmented virtuality. Do you know what this is? Have we talked about this at all? So this you hear a lot, right? AR. AR is going to change the world, and Pokemon Go, and blah, blah, blah. Augmented virtuality is an interesting place and something that's been working on now. And I'll explain it by way of saying, we can think of augmented reality as the main world that we're in is the real world, and we add some virtual content. So I'm in the real world, and I see the Pokemon characters in the real world. So my main world, if I look around, I'm going to see the real world. And I add in some virtual stuff. Okay? Augmented virtuality is my main world is the virtual world. So anywhere I look, I'm still going to see the virtual world. And I add in real world stuff. So for example, my arms. Maybe what I do is I bring my arms into the virtual world, and now as I move around, I can see my hands and my arms, right? Or an object that I want to bring in, like, oh, great, I now have this physical thing. So you might have cameras that have scanned this object, and now I can bring this real object into the virtual world. But the main world is still this fantastical place that's completely computer generated, okay? And so some people do research in this. You hear less about it, right? Because AR is really, really, really hot. But these aren't discrete locations. So in other words, they really bleed into each other. When do you transition from this to this? It's kind of a messy transition. Or how much stuff do I need to add? Does everything have to be purely virtual? as soon as I add something physical, am I now here? So it's really hard to make that distinction. So we can say that systems are more AR-like or more AV-like or VR-like or they're real-world systems, but really this is a continuum. So these things get mixed a lot. And if all the visuals are virtual, but I'm holding a physical object, usually this is thought of in the visual domain, but we don't need to just think about visuals. So we can think about these things along this continuum. So you understand? So you'll see these terms come up, and this is a much more interesting space, bless you, to work in than purely virtual or purely physical. It's just richer, and there's much more cool stuff going on and more solutions you can come up with. So here's an example. So 3D cinema. So this is a relatively old picture, but these are people sitting with 3D glasses watching a movie, and so they see something going on. And so this, we can say, it's a computer-generated environment. It's three-dimensional. It's not really interactive. It's passive. I'm sitting and watching a movie, right? It could give me a sense of presence, right? There's no real-time feedback. I'm just watching a movie. So this is not really virtual reality because there's really no reaction to anything that I do. But again, you can argue about all of these things, and that's not really the point. It's really to look deeply at it. So how many of you read books? So like for fun, okay. And have you read like on a train or on a plane or something like that? And have you ever had the experience that you're so engrossed in the book that you're like, I don't know, they just came by with the wagon to sell me some stuff. Been pulled out of this book that you've been reading, right? So in that case, you're present. That's really a sense of presence because your mind has totally bought into this situation. So if you think about reading a horror story, like reading a scary book at night, alone, at home, with the window open, that can get kind of scary. If you're reading the same book on the beach on a sunny day with lots of people around, blah, 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 it's a very different experience. And that, again, has to do with this notion of immersing the person. Again, in this dark room, you're surrounded, you're actually being immersed in the story even more. Whereas, so we can generate this sense of presence with very, very low technology. Black words on a page will actually allow us to become very present. And that's because there's lots of imagination coming involved. So the 3D cinema maybe isn't a good example. This is one of the very early headsets built by NASA, and it looks like this image was flipped anyway. And it had voice input, it had gloves that you could actually use to interact. And so we think about this exploration. This actually would fulfill all the requirements. It's interactive, I can move stuff around, and it might generate a sense of presence for us. So we can think about this kind of a diagram of VR systems. So we have a VR system here. We have the user, or multiple users, and somehow we have this loop around. The user might explicitly make some input, like press a button or say something, right? Or throw something. So they make some input into the system. We have some technology that tracks you. So it's monitoring the position orientation, or it's tracking the buttons, what's the state of the buttons, pushed, unpushed, or it's a joystick or something like that. And so we have this user tracking that's done, and that we can generate movements and things into user input. It could be a gesture, right, or a grab gesture or something like this. So I'm tracking the user in some way, and that produces some inputs that the system then understands. The system then has different output modalities. So it'll generate an audio signal, like two things hitting each other, or visually see something move around, and that will then display that back to the user, okay? And this notion of display, and I'll use my triple air quotes, this notion of display is really not limited to visual displays. So you can have touch displays, and you can have audio displays, and these things, okay? So you can think of this is what we're talking about in real-time interactivity, is that the user does something, it's sensed by the system, it makes some change in the virtual environment, and then there's some stuff that's sent back to the user in terms of updates of the state of the system. So tracking, we can think of very, I'll go away. I tell you, the Mac is becoming so much like Windows now. Oh, did I say? Anyway. So there are lots of things that we need to track. So some of it is we're trying to estimate the user's head pose. This is a lot of what we do in VR. It's like allows you to, if you have these two displays, when the user turns their head, you update the graphics to show them what's over there, right? When I move around, we actually update the graphics to let me feel like I'm moving around in a space. So this requires some amount of head tracking. So we have some pose estimation for how their head is oriented, and some position estimation for where their head is. So often this is done in 6 degrees of freedom. So degrees of freedom are one variable or one dimension that we can move along. Some systems only have 3 degrees of freedom, so they only do rotation. They don't do any sort of movement. So the Gear VR or Cardboard or these types of systems, they actually don't allow you to track the user's head position, only the orientation. And that's good for some things. Everything you add adds more cost and complexity. So one question is how, we're talking about we need 3D, we want wide field of view, we want some motion, maybe we want some smell, some wind, some vibration. And the question is this new? And actually in 1962, there was a device that was marketed and sold called sensorama. And sensorama is a revolutionary motion picture system that takes you into another world. So it had all of these things built into it. You can even call this number and buy it. And it simulated a motorcycle ride. So the seat vibrated, and you had these handles that you turned. You had sound around you. They even put some like smell. I don't know what it was, diesel or something. There's some sort of smell coming at you. And it was in color, okay? It was in color. And so you could actually try this system, and this was revolutionary. People really felt like they were riding a motorcycle. This was one of the very early systems that people giving talks like this always bring up, in that what we're trying to do has been worked on for a long time. So there's been some fascination with this. So in general, when we talk about interacting with systems, there are several things, or what we've tried to do is, on the desktop, we have things like point and click, drag and drop, scroll bars, different types of radio buttons, text input. So we have these kind of very basic tasks that we carry out on the desktop. And so some work in VR has tried to say, well, what are the basic things that we need to do in VR? Right? So any sort of application that you use, Microsoft Word or a browser, they all use button clicks, double clicks, right? There's kind of these standard lexicon of how you talk to the computer. And so one body of research that has been very instrumental has looked at, is there a way for us to break down virtual reality interaction into these really low-level things? And then if you provide support for all of these things, you can build anything, because these are the basic building blocks. Just like on your phone, you know that there's tap, there's long tap, there's pinch zoom, there's swiping. These are the basic lexicon, and every application, every app on a phone is built on these sorts of things. If you try to do something else, like, oh, I'm going to tilt the phone. Well, you could, but probably people aren't going to know what that is. They haven't really done it before. And you see it sometimes, oh, look, I can tilt, I can play this game. That's a really novel thing. So the question is, at some point, these gestures, like a swipe gesture, that becomes something that everybody understands and is generally useful for many applications, okay? But that didn't exist 15 years ago. It just didn't exist because we didn't have this technology. So everybody understands pinch zoom. Everybody understands two-finger rotation. But that didn't exist. So the question is, in VR, is there a way for us to come up with these standard things that we can build on? Sorry. So some of the things we need to be able to do is to select an object. So on the desktop, this would be pointing. I want to be able to point to something. Move my mouse, point to something. In VR, how could I do that? So if I wanted to select that water bottle, how would I do that? You guys have any ideas? I want to select that object. What do I do?
Press the button.
Hmm?
Press the button.
Okay. I want that one. How do I? So I can point at it. Okay. Good. And then I press a button. Okay. Good. So I point at it, press a button. Okay. How else could I do it?
Teleport and just grab it.
Okay. Teleport over there. Grab it. Okay. Good. So we have two ways to do this. What else? How else could I do it? Hmm?
Code. You put the code and select it.
Okay. So I could type in water bottle number 7. Okay. Yep. I can do that. All I'm doing is I just want to select an object. How could I do that? I want that water bottle.
Just see it.
I could say it. I want that water bottle. So I can combine this gesture and my voice. You guys understand that, right? I want that water bottle. Maybe you don't know which water bottle I'm pointing at, but if I say that I want that water bottle, all of you understand what I mean, right? So why can't I do that in VR? I should be able to say, I want that water bottle. And the system should say, yep, here it is, Rob. Here's your water bottle, right? So I can select it, okay? I could also just walk over there and pick it up, right? Say, that's the one I want. I could say, hey, could you throw me that water bottle? Bring that water bottle over here. Right? I could tell the system, use the force, right? I could use the force, concentrate, and whoosh, it's going to come here. Why not? You laugh. I can be a Jedi hero if I want to in VR, right? We actually wrote a paper on that. It's called Jedi Force Extension. And basically what you do is you gesture and you bring it towards yourself, and then you tilt your head slightly, and it comes towards you. And the head tilt is like a concentration metaphor. So you can pick it up and you can move this way, and then you concentrate and it'll just take off in that direction, right? Or you make a scaling gesture and then you tilt your head a little bit and it gets really big, right? It's kind of cool. Because you can, that's why we try these things, right? So just this very simply, just selecting an object, there are lots of ways that I could do it. And the question is, I could also use a laser pointer. So you said pointing, I can point, but I could also literally draw a rod coming out of my finger that allows me to, so I could like make a sound and a vibration. Every water bottle I touch, it'll go, right? So now I'm being helped. Okay, now I'm intersecting. Maybe it glows, right? You give some feedback about which one you're selecting, and then maybe I make a gesture or push a button. So I could point. I can maybe skewer it. Right, this notion of having a skewer, and I could stab it and then pick it up, right? Lots of things that you could do, and all this stuff has been tried, by the way, just so you know. So that's only like selecting. I haven't done anything with it, right? So if I want to drink from the water bottle, what do? I probably want to do something. That one looks like it flips up, and then I got to do this, right? If I want to change its color, because I can do that in the digital world. I want to make it red instead of greenish. Green? Is that green to you? Okay. If I want to make it reddish instead of greenish, what do? How would you do that? How would you change the color of that object? Paint it. Good. How? Like, what do I do? Tell me what actions I take. I have a virtual paint can, and I dip my brush in, and I go, okay, so now it's red. Good. And then I can go, and then poof, they disappear. That's actually a great game. Let's make that one. Okay, good. So I could paint. How would you do this on a desktop? Change the color of an object on the desktop. Has anybody done this before? Like in Word or any sort of CAD package, or how do you do it? What do you do? How do you change the color, though? Like, how do I tell it the color I want?
Select it and use a color wheel.
Okay, so I could select it. I could pop up a little thing that says, hey, Rob, pick a color. And then I could maybe move around this color wheel with, again, some sort of something, pointing or something. So I can move around, and then I could watch the bottle change color as I move around. And then I could say, that one goes away. Now I've changed the color. Right? Perfectly fine. These are things we just don't know how to do in virtual reality. We don't know how to do these things that there are RGB sliders. You see this sometimes. Yeah, change the RGB values or use a color wheel or choose from a palette. Maybe you have 10 colors you can choose from. We just don't know how to do these very simple things in VR. It's new. And that's hard. Navigation. Maybe I'll give a talk later on about navigation. So navigation is knowing where I am, knowing where I want to go, and figuring out how to get there. Okay? So navigate. Okay, I want to get to the Ancestral. I want to go have some lunch. Okay, so where is it? Okay, so I got to figure out, so you understand navigation. GPS, right? We use GPS to help you drive somewhere or walk somewhere. So navigation in VR has two components. It has a wayfinding component, which is understanding where I am and where I need to go, and a locomotion component. A locomotion means how I actually move to get there. Do I take a bus? Do I take a bike? Do I drive? Do I walk? So these are two separate but related things. It could be that I teleport, right? Teleportation is common in virtual reality. I get this little, again, it's a different talk, but I can move around more or less efficiently using different control techniques with my controllers. I can fly maybe, or fly. I could do this, make this gesture, allow me to fly around. But that's separate from really understanding the world around me, where I want to go. Okay? And there are, teleportation, for example, is a really bad way to go somewhere and remember how I got there. Right? Understand the route that I took, because I just disappear from one place and appear at another place. It's like getting on if you guys have ever ridden a train or a subway, going down into the subway, going somewhere and then going out, you come out and you have no idea how you got there, where you are in relation to where you were before, right? Whereas if you walk, you see things, you're walking, you see the sun, you have all these markers to show you where you're going. So there's actually two different things. System control is allowing me to change parameters of the system. So a properties box or these sorts of things. Symbolic input is typing or putting in numbers and these sorts of things. So speaking, how do I say, how do I send an email in VR? Well, I don't really have a keyboard anymore. I'm really efficient. Well, some people are really efficient on a keyboard or with this, but I don't have this in VR. So how do I enter text or numbers? Hard problem. You can use voice. There's lots of different things you can do. Some actually not that well explored. And then embodied interaction is, how do I represent myself? So how do I show my avatar? Right? So this in VR, we have it on social media. We have a little bit of this. Like, here's my picture of my icon and things like that. But that lets other people know something about me, and it may or may not be me. It may not even be a person or whatever. But in VR, for us to have a conversation or for us to see each other, you have to understand something about my body and where I'm looking or where I'm pointing, so we can have some sort of meaningful interaction. And controlling your body is also something, and representing that movement is actually something really important in virtual reality. So you see these problems? So all of these have nothing to do with a particular application, but are really important for almost every application. Okay? Just like we do on the desktop, these design decisions. And there are ways to evaluate things. Movement, for example, when we're moving around in VR, efficiency could be a really important measure. How quickly can I get there without bumping into stuff? But it might be more important in some applications to know how I got there, to really understand the spatial layout, right? And that's a different measure of goodness. I can get there quick, but man, it takes me like 5 minutes to figure out where I am, right? That's just a general example. So in terms of visuals, we have a bunch of different approaches. We have some projection systems. So this is what's called a cave, and this is a silly recursive acronym. This is a cave automatic virtual environment. So it's a recursive, anyway, it's recursive in terms of the way it's laid out. And a cave is a cube that you stand inside where all the walls are projected, the floor and the ceiling, and everything is seamlessly connected. So you can think of the holodeck in Star Trek. I'm standing here and I'm completely surrounded. Anywhere I look, all I can see is the virtual world. Okay? And the user's head is being tracked, and the graphics are being drawn from my point of view. So everywhere I look, the system is understanding where I'm looking. And as I move, all of these walls, all of the projections, everything is being updated to be perfect from my point of view. Okay? And these systems have been shown to be really good for some things and not so good for other things. And we'll talk more about that later. The other thing you could do is make it wrap around this way. So some sort of holo stage or some semi-cylindrical set of panels. The responsive workbench, this is also one of the really early systems. This is similar to a cave, but you only have two surfaces. And you're tracking the users where they're looking at the surface. And what this gives you, you can actually make an object appear to be in front of the display or behind the display. Because of the way they're working the stereo, they're making the graphics and the stereo vision, you can actually, they're tracking your head and they just update the displays to make you feel like you're looking at something like this. And we have, Harish has a system on his desk that does something like this using a single display. And so this kind of uses stereo imaging to allow you to see things in 3D. And the way this works is they have often two projectors, and they're switching off between a right and left, so they're flickering a lot. They show you the left eye image, the right eye image, the left eye image, the right eye image in very, very fast succession, and they close and open the left and right eye. So when the right eye image is being shown, the left eye is being covered with these stereo glasses. And when the left eye image is shown, I cover the right eye. And they do this in synchrony with each other, and that allows my left eye to only see the images that are correct over here, and the right eye to only see the images that are correct over here. So it allows me, if you guys do this now, please, if you put your finger right here in front of your face, and you close your left or right eye, you can see your finger bounces from side to side. Nothing really magical happening. But what they do in the graphics is they calculate what the view should be from each eye, and they only show that eye the image that it should see. And this is a very important cue for things that are close. For things that are far away, it makes less of a difference to us. So, and this is actually important from a design point of view, that this stereo doesn't matter past a certain distance. The difference in the images is too small, and it doesn't affect our ability to really understand the scene as well. But it's really important close up for many applications. And there's lots of technology for that. So again, a long time ago, in 1995, Nintendo came out with a Virtual Boy. Yay! So this is a head-mounted display sitting on the table, and you put your head up to it, and it shows you unbelievably impressive graphics. So it had 4 levels of red. That's what it could do. And so you could do things like, this is the kind of things that you would see on it. And again, they would be showing you each eye independently. So you get some stereo effects here. Didn't really take off at the time. Fast forward, the technology we have today. This is not today. This is the late 90s. This is a very early headset that actually had 2 CRTs. So CRTs are what we had before these flat panels, old televisions. And these were about $70,000 US for these headsets. And they were not that wide field of view. It was okay. So a lot of high-end applications would buy these units. So some of the major problems are that these are big magnets because of the way the technology works. And so you actually had really big magnets near your brain for a long period of time. And anybody who knows something about that is, it's not good to have a lot of magnets near you for long periods of time. These were pretty powerful because the displays had to be powerful. So anyway, this unit came out about the same time, and it was about $12,000 US, so much cheaper, but wasn't as high quality. The experience wasn't as high quality. But a lot of the research labs use this unit to do a lot of the experiments. And I won't talk too much about the next one. So the nice thing is, so this is kind of in the 90s. So this is the first system I ever used was in 1994. I played Doom on this for way too long because there was a patch that allowed you to play this 3D game. You could see it was about $700 US. It's got the resolution and things, so it's about, it would be about $1,200 today. About the same time, the Virtual I/O glasses came out, and these had two displays, so the displays were shining here, and they would be reflected into your eyes. They also had a shield that would go on front to make it opaque. This was a commercial headset that was used a lot for location-based things. And again, you can see the resolution here is higher than these. The price is still about the same. Sony came out with its own version of these things, again, thinking that you're going to use this all the time. It had a Sony price tag as well. So that's kind of, I would call the Sony tax that you pay. It had a nice resolution. We have a couple old one of these in the storage room. This we've actually used a lot in the recent past. It looks a lot like this one. So the thing about these headsets is the company would come in and they would revolutionize the industry. They say, this is going to be the future. And then the 200 or 150 research labs around the world would buy a bunch of units, and then the company would crash because there wasn't a market for it. So they would come out and they'd be like, this is great, you're going to love this. And then the company would fold. And then a couple years later, the next company would come along and they would sell a bunch of units. We would all the research labs would upgrade our equipment, and then the company would fold. And so you saw this wave. I've definitely seen at least two big waves of how VR was going to change the world. It didn't really happen for various reasons. But you see these are not very immersive. So they're not, these two are actually pretty good. The field of view wasn't great. But these are, you can see a lot of the real world, right? Because they're just kind of two displays hanging out here. We'll pull some of these out later and you can see what they were like. So this, again, the resolution is not bad. The price is still about the same. So for all of these, the price is about the same. The current generation has seen a really big explosion. So around about 2015, these units started to come on the market that were very much more sophisticated, much better quality, and still keeping the price down to something within reason. So the open source virtual reality headset that came out, we have a couple of these. And the idea was to really come out with a very inexpensive, adjustable, open platform that people could build for. The Oculus Rift came out in March 2016. Again, really good specs, really wide field of view. So field of view is very important, so you don't see the edges of the displays, and still about $600. The HTC Vive came out, and the Vive Pro, which has been since released. So this was April 2016. Very similar specs, similar field of view, similar price, and just competing competitors in the market. Sony came out with its PSVR, again, similar specs. And of all of these, this one has sold many more units than anything else. Okay, so the PSVR, why do you think that is? Why do you think Sony's unit has sold so much?
Well, the price is one thing, and the other thing is the console, the PS4
Okay.
can render
Okay.
the device, and you don't need a high-quality computer.
Okay. So good. So Sony see this as a peripheral for your PlayStation. Okay. And we're used to buying things like gun controllers or driving seats, steering wheels, if we're doing this sort of thing. So if you think about this, each of these requires me to have a pretty powerful PC, and then I have to, on top of that, pay for the unit itself. Whereas with Sony, at least on paper, I can use my existing PS4 and I can hook this up. So it was very attractive to some people, especially young people who really wanted this at the holidays, right? So there are many more units sold there. The other really big thing that's happened is content. So there's a lot more content in this wave of VR. So there are a lot of game companies that have jumped on, and they're building content. it used to be, in the previous wave, we were writing all of our own software to run on these devices. Now you have game engines like Unity and Unreal where it's a one click to get your application running on some of these. So all of the heavy lifting of tracking and figuring out how to set up the displays so that the right eye and left eye look, all of that is being taken care of. So the tool chain is a lot better now, right? So you have reasons to buy these things, which you didn't really have before. And you have, and together with that is that developers have a much easier path to getting their content out there because they understand the tools already. They've already been using Unreal or whatever to build their content. Now they can release to this. There's still lots of garbage they're trying to sell that's being sold for these units, but that's a design question. Is some people are just trying to port their standard games and it's just not working because it's a different platform. Okay, so it's a really sweet time right now because all of this is very accessible, and we have all of these units in the lab for you to use. Microsoft has come out with a mixed reality platform. So there are a lot of companies that are trying now to really get into the market and trying to really produce hardware that people are going to want to buy, people are going to build for, and there's going to be content for it and things. And so Microsoft is trying to frame the conversation around HoloWare. So this notion of holographic imagery. The HoloLens is not holography. But that's fine. That's what they're calling it, is that this is holographic things that they're doing. So they have this mixed reality platform that vendors can then, so you know, Hewlett-Packard, Acer, Dell, they can all produce units that are based on this same stack of hardware. So they look very similar. They have a lot of the same things, right? Technologies built into them. And the idea is then to have like the PC of this world. So instead of having all these different units like we had here, we're going to have one platform that everybody can build to, and we'll just remove all of the differences between them so that we can have multiple vendors producing hardware, and the software people will produce for them because they know that there are all these vendors producing hardware, and all the software will run the same. And then again, you see the price points and the tracking that's available, resolution, and so on. So the next thing that has happened is that we've had, or in parallel with these VR headsets that you connect to a PC, are these standalone ones. Okay, so these are things where I take my phone and I put it into this thing, in this case a piece of cardboard, and now using the sensors on the phone, and the phone now knows it's in a headset, so the screen will be split, and the right eye and left eye will be displayed here, and physically there'll be a barrier between them so that when I look, my eyes are getting the right information. And now suddenly for $30, I can do VR. And things like the New York Times, when I was living in the States, we were a Sunday subscriber to this newspaper, the New York Times, and in one of the Sunday editions, they sent every single subscriber a VR headset for free. It just came in the newspaper. And that's a lot of things that they shipped. And actually, I'll be right back. Let me just grab mine. So this is what they shipped. So imagine inside your newspaper, you open it up and this is what you had. Okay? And this is that. And it comes with instructions, fold here, bend here, tape here. It comes with everything you need. And then you just put your phone in, go to this website, download content, VR. Okay? Pretty impressive, right? If you want to get 1 million people using VR, just send them a free headset. Have them drop in their already powerful phone, make content for them. And so you can, please don't open it, but you can check that out. And what they had is the New York Times is really good at making news stories. So what they did is they hired some really good people who understood the technology to make 360 videos, and they sent them out in the field, and they made really amazing news stories that you consume using this device. Okay? So So now you have content generators that are really good at making content for a completely new platform, and you've now sent everybody the platform. Okay? So it's a very impressive model to think about. Google, who developed this, Google Cardboard, and there's plans and you can go online, and I literally took an Amazon box that I had laying around and just cut one out. You can do it all yourself, actually. It's just cardboard with a couple, you have to buy the lenses, but they're like $10 or something. So they also have ready-made versions that are really the same thing, only more rugged, right? Which is what this is. So for 150 in New Zealand, this is 200. This is a much higher quality device that you put your phone in. This is a Samsung device that's based on the Oculus Rift, which is their non-standalone version. But this Samsung devices require Samsung devices. So this is a headset, but you have to have a Samsung phone in order to use it. This one, you can just put kind of any phone that will run what you want, right? So Samsung, you can understand Samsung's point of view. They want to sell more hardware, right? So that's fine. And since then, we've had a number of different things. So Oculus came out with its Go, which is, again, a standalone device and allows you, again, we have some of these in the lab. And all of these really are trying to make this accessible. And some of these will go away. So we're in the boom phase right now. Some of this will go away at some point in the future. Okay, so that's a very brief introduction. I just have a couple more slides and we'll take a break. Any questions up until now? Is this interesting? Okay, again, it's a very fast movement through the space, but so there are some problems with VR, and some of them have to do around simulator sickness. And again, this is an old paper. Okay, so these problems have been looked at for a long time. It's just that the user population was much smaller. So a lot of this work was funded by the US military because the US military was really keen to use this for training, different kinds of training. So the idea is, let's look at the science behind people getting sick in virtual reality and see what we can do. And so they went through and they made a relatively exhaustive list and a questionnaire to measure these sorts of things. So they ask you things like general discomfort. Tell us generally, how fatigued are you? So tired are you feeling? Do you have any headache? How are your eyes feeling? My eyes are dry, or I feel eye strain. Difficulty focusing. More water in the mouth, sweating. Like you see people sweat a lot when they're really engaged or something. I'm feeling nauseous. I have difficulty concentrating. Fullness of head, I still don't understand what that is, but fullness of head is nothing. Blurred vision, dizziness, with eyes open and eyes closed. Stomach awareness, burping, it's very important. I guess burping is one sign that you're feeling sick at some point. So this is a problem. So when you're designing systems and when you're designing some application for use, you really need to think about these things. Has anybody ever gotten sick in virtual reality, or has anybody used virtual reality and gotten sick? So a couple of you. And this is a very interesting topic because there are lots of things that cause these problems. And not doing those things helps reduce it, but it's hard to actually reduce it completely to nothing. So some of the things that cause this are latency. So I turn my head and the graphics don't quite line up, right? So I have this latency. And even small bits of latency are noticeable. So we are very highly trained machines. So we move our heads, we look around, we expect things to be where they should be when we move our heads. And we're very, very adept at seeing when something is off, okay? So that's a problem. Miscalibration between tracking. So I'm going to reach out and grab something. Well, if the tracker thinks my hand is over here, and when I reach out, it's going to show me this. And that's actually wrong. My hand is actually here, not here. And this happens too much when I'm trying to see things. I'm actually going to start to feel pretty bad because I'm going to be adjusting myself. The thing that we know about humans is that we are really adaptable. So if something is off, we will actually adjust. So if you and I are playing catch and I'm throwing something with you, you're throwing it back to me, and I add in some latency, we're going to be really bad for a little bit, but we will adjust. And we'll actually get pretty good at dealing with lots of latency and, oh, I need to reach over here. We will start to move a lot earlier, or we will adjust our behavior. And so the good thing is we can adapt. The bad thing is we will adapt. So when you take the headset off, now you're adapted. And now you're supposed to drive a car. But the world I'm in now doesn't match the world that I've adapted to. Right? So I'm going to feel sick. I'm going to get into accidents. There's lots of things that can happen. And again, this isn't studied very much, but any experience you give somebody changes them. And the question is, how do you bring them back so that they can work in the real world like they need to? Field of view.
There are some studies about secondary effects using VRs after a couple of years.
Right? After, yeah, there are some, and they're really hard to do, right? Because there's so many individual differences between people. The applications that they're using are different. So there's definitely work on how people have been changed by long-term exposure. But there isn't a lot of data out that's generalizable to a lot of things. So you can say headsets are bad, but it's hard to know. Or this, your latency needs to be this low. These things are really hard. So all of these things can lead to these problems. The other kind of interesting thing is actually women seem to be more susceptible to negative effects of wearing these VR headsets than men. And it's still unclear why. But in general, women tend to get sick more than men wearing these head-mounted displays. And lots of researchers, both men and women researchers in the VR field, are really trying to figure out what's going on.
There is something about the age.
There's lots of factors. So age can definitely be one. I've had students who, they ran out and bought a VR headset, and they said they came back the next day like, I get so sick. So they spent all this money, bought this headset, and they just get sick. They're like, it's terrible. A month later, because he just forced himself to keep using it, he had adapted. So he didn't get sick anymore. And maybe that adaptation doesn't happen well when you're older. I don't know. I wouldn't know because I'm not old. So there's lots of contribution to this latency problem. So there's technical things like the sensor is just not fast enough. There's other things going on. So the user makes an action. The system has to react, has to capture that information, react in a certain way. And there's lots of places in this system where more latency can be put in. And it's always added in. So there's a delay, and the camera that's tracking my movement has some delay in processing its output to produce, oh, Rob's arm moved like this. So just that processing adds some latency. And then the application has to get that data and do something interesting with it. There's more latency there. Then I have to draw the system or display the system and update that. There's some display there, some latency there. So all of these things add to some amount of latency. And so a lot of the goals around latency reduction, it looks at each one of these and tries to reduce them down as low as they can go. And actually, Anthony's done a lot of work in latency reduction. He's a great person to talk to about this. So to sum up, the technology is fairly fragmented. So we have various input devices. There are cameras, the Kinect, for example, other depth cameras will capture my movement. So it will calculate my skeletal layout, pose, every frame, and send that information to the computer. But there's some noise, so it might not show my hand moving smoothly. It might show my arm moving like this because there's noise, the lighting wasn't good, or there's interference of some kind. So there's some problems there. There's no real standard way for me to use that information. So when I want to move around, there's this notion of walking in place. So I can teleport, or I could just take steps. And as long as I'm tracking the person's step taking, I could actually translate that into movement in the virtual world, right? So that's good because it's more like I would do in the real world, and it's bad because I might get tired, or I might bump into something because I had this headset on. There's lots of bad things to it, and there's lots of good things to it. But it seems like something good to try. So there's various types of input devices, and all of the headsets that I showed have different types of devices. So they have these controllers. The controllers have these buttons, or these joysticks, or these different triggers, lots of stuff, not a lot of standardization. And then there's a lot of different types of display systems. So here we have a wraparound display called the SimPit that we use. We also have a lot of head-mounted displays, so these VR headsets. There's phone-based ones. So the platforms are all different, and building for them is kind of a mess right now. So some takeaways is that a lot of us really start by going back to what we call human-computer interaction first principles. So if you think about this, a good design really requires you to look at both the technical constraints, which we talked about today, and the human abilities or human constraints. So these two things are extremely important. It's not about the technology only, and it's not about the person only. We need to come up with interaction metaphors that people understand and that are useful. So people, this notion of scrolling, I mean, how did that happen that this led to a zoom gesture? I mean, it makes no sense. All I'm doing is moving my fingers. If you look at it abstractly, it makes no sense that this would be translated into some sort of zoom gesture. But it has. So are there similar things that we can do that says, like, this is a gesture that brings an object to me? I don't know. Like, how do we do this? So there's still a lot of challenges here in kind of making this kind of standardized platform. So in the end, from a design point of view, what you want to do is you want to look at the big three, which is the user, task, and environment. So the user has certain abilities and has certain knowledge, certain background, certain age, or whatever. There's a task that you're going to have them do, and the task requires some amount of precision, right? So if I need to pick something up and move it, that requires some amount of precision that I can do in the real world, but maybe the technology doesn't allow me to do that in the virtual world. The tracking isn't that good. So it's going to be, my hand is going to be moving like this because the tracking is really bad. So I can't really make a task that requires this amount of precision if the technology doesn't support it. So maybe there are some things that I just don't want to do. You don't want to do this in VR. The other things so for example, in 3D modeling, you often have a 3D model, and you can actually move a vertex. Like you want to take this vertex and stretch it out a little bit. You want to shape this ball of clay into a creature of some kind. And you can move vertices that are connected, and we actually can do that pretty well with a pen and tablet interface or with a desktop interface. When you start to do that in VR, it sounds really great. Like you can take your controller and you can walk up to this and you can grab it and you can move it. And it's really amazing to be able to push and pull on these objects that are floating in space, and you can model this thing. The problem is your arm gets really tired by doing this, right? So you can do it, but you probably can't take it and release it exactly where you want to release it, because there's going to be some jiggle, right? So you grab this, you move it, and you release. Wait, no, it's not right, because I can't release without shaking, and you do that for an hour, and you're going to hate your life, right? So these things that the desktop works really well because I'm on a desktop, right? My hand is resting. I can release the device, and it's going to stay where it is. So this notion of clicking with precision is very easy when you have the support, whereas if you have somebody doing these things, you really don't want to have them do that in VR. Even though it's cool, and even though there's some reasons why you would want to do it, it's very hard to actually have somebody do for a long period of time. So, and that's the last thing, is the environment. So people might be mobile, they might be sitting down, they might be in a big space. So taking these three things, looking at and analyzing the user, the tasks they're trying to do in the environment, will lead to good solutions. So let's take a break. Take a 5-minute break, come back at 15:15. And think of questions while you're on break. Rory, can you hit stop something over there? Yeah, did it pause? Okay. Is this helpful for you guys? Just say no if it's not. Is this kind of what you were looking for?
Yeah.
This okay?
Do we have a chance to use this UVR facility?
Yeah, you'll have a chance to try it probably maybe next week. Yeah. Yeah. You can step out if you want.
I was just talking to one of the students before. I'm not sure that anyone's told them about the kitchen facilities and where the toilets are and things like that.
Which students? Like these guys?
Yeah, the whole lot.
Oh, okay.
Yeah, yes. And so I just thought may pay to just let
Yeah.
them know who can
Okay.
use the kitchen
Okay.
rules and things like that. But
Yeah, we'll
I think
do.
most
That's
of them
good.
have figured out where the loos are. But
Yeah.
So,
Okay.
one
Yeah,
of the
we'll
MHET
do that.
students was just asking. I was like, oh.
I'll do it before we turn on the recording, maybe. Before we start recording again.
The MHET desks are ready to go too if they
Oh,
haven't
okay.
jumped on them
All right.
already. Yeah.
That's great.
Yeah.
Good. I think Greg can, maybe after the lecture they can come out. Hey, Greg? So we're done about noon with the MHIT students. Can you hang out for a little bit before going to lunch just to show them their desks? Yeah? Is that all right? All right. Thank you. Everybody's here. Can someone unpause over there? Do you see where to do that? If not, okay, good. Hi, everybody. Welcome back. So I'm going to take you through hopefully, a pretty quick tour of two of the sensory things, which is audio and haptics. I should say that in general, we are visually dominant as a species. So visuals and audio are the primary means of how we have survived. So understanding the world around us in the early days involved staying away from predators and trying to find food and these sorts of things. And so we have evolved. These two particular senses are very strong for those main reasons, is they have allowed us to survive as a species. And then there are other things that have developed to support us. Obviously, we need to eat, so our sense of taste has helped us avoid eating things that might be harmful to us. Smell has also allowed us to both find and avoid various things. And the sense of touch is really interesting. One of my personal favorites, mainly because it's so difficult to study. It's so rich, and so we'll talk a bit about that. And but I want to talk about audio first. So in this, we're really concerned with kind of the other technologies beyond visuals. There's lots of things around visual appearance that are important, but they've really been worked on a lot, and audio and haptics have been worked on less, though audio has definitely been worked on a lot more than haptics. So audio displays can be used in VR. Visuals, we know that there's objects in the scene and we can move our head and they're going to move around. And you know, if I'm looking at you now and I turn my head, oh, I'm not going to see her, right? And that's because I'm looking over here. And with audio, so with visuals, we have this ability to be able to direct our gaze at something. And with audio, we have this notion of spatialization and localization. And these are related. So spatialization is that there's a source for a sound. So in this case, my voice. Or there might be there might be air conditioning running somewhere and we hear the air conditioning going. Or the windows will open. And those will be coming from specific locations. And so in the real world, typically those are spatialized sounds. So they're coming from somewhere, okay? Things like music that I'm listening to that's just kind of, maybe there's a bunch of speakers around and the music is just playing. It's not really coming from any specific place, it's just there, okay? So this is kind of unspatialized audio. And from a computational point of view, if I can see you in the virtual world and I can hear you in the virtual world, I would really like your voice to come from there, as opposed to me just hearing it in a non-spatialized way. So me seeing you here and hearing your voice come from there is more what I would expect in the real world. So it's easier for me to believe it, or for my imagination to buy into it, if it matches what I expect. And that's spatialization, is taking a sound or multiple sounds and putting them in the virtual world so that they sound like they're coming from a certain place. And you might say, but you know, if I only have headphones, how do I do that? And the answer is science and engineering. So what we do is we figure out how we hear in the real world, and we try and replicate that somehow in using digital content. Okay? So that spatialization is putting things in the world. So this is the technology part, is figuring out how to take a sound and place it in the virtual world. The human part is the localization piece. So localization is the ability of somebody to recognize that something's coming from a certain place. Are you okay? If you need to cough, just let it out. It's okay. Yeah? Are you sure? Okay. You look like you're suffering, so I don't want you to suffer. So different people actually have different abilities of localizing sound. So there are some people who are just not good localizers. Even though the sound is spatially placed, you know, I could have a speaker right over there, they just can't tell, or they're just not that good, or maybe they're plus minus 40 degrees, right? They can't really tell. So the localization is my ability to detect the spatial location of a sound. So this is really a technical thing, and this is really a human thing, localization. Okay? And sometimes spatialization is not important. And sometimes the ability to localize a sound is also not important. I don't need to be that precise. And the reason is, if I see you, even if your voice doesn't come from over there, my brain is still going to have some indication, I think he's over there, right? So we don't need to get the audio exactly right. It just should match up with what we expect, right? So even though somebody's a bad localizer, they have vision to fall back on. And that's a good thing, right? Okay, so we think about, there's been a lot of research on the properties of audio displays. So we think about the number of channels. So this is, let's say, stereo. So we have two channels, a left channel and a right channel. Could be more. There could be some sort of sound stage, like what are the properties of this room, right? So actually, if you hear, there's a pretty bad echo in this room, even though I just had them install these sound dampeners. There's a pretty bad echo in this room, and any sound person that comes in this room is like, this is a terrible room to give a lecture in. It's just not, it's not designed for this, okay? And it's really, the acoustics are pretty bad in this room because there's lots of reverberation. I can hear it very clearly. And then, so there's localization, there's masking, we'll talk about some of these things, amplification, and then there's some logistical things. It could be that the environment I'm in, I'm outside walking around, maybe it's just really noisy. So I can use all the audio I want in the experience, but they can't hear me, right? It's a problem. User mobility. If I'm using speakers, I can't really go outside or move around. I might have no way of tracking where the person is. So in visuals, if I'm tracking the movement of their head, I can change the visuals. I can use the same information to change the audio. So I can make the audio sound like it's stationary in the world, even though I turn my head. I just adjust the audio, right, the amount going to each ear based on the orientation of the head. So you probably know that if a sound source is right here and I'm listening to it, it's going to get to this ear before it gets to this ear. So very simply, I can just adjust the delay between the time the source is fed to the right ear as it is to the left ear and give some indication of the location of the sound, right? That's a very, very quick and dirty approach to changing the sound. And there's lots more sophisticated things that can be done. So there's lots of these issues that you need to think about when you're making audio displays. So channels come down to things like 5.1 audio. So have you heard of 5.1? Or 7.1 or 2.1? So the idea here is these are the number of kind of wide range, broad range speakers that I have. And the 0.1 is typically some bass or some very low frequency things. And in general, people are very good at localizing these mid to high frequencies, and we're really bad at localizing low frequencies. So the 0.1 is typically there's a big woofer that's put somewhere in the corner, and it doesn't matter that it's in the corner because won't be able to tell where it is anyway, but I can put a lot of power into it because it's a big unit. Whereas I can put smaller speakers around, and that will allow me to better utilize the space and still allow people to localize where something is coming from. So if you think about these systems, if you go to a movie, like a high-end movie theater, they'll have 36 speakers in the theater. And the audio is laid out such that when the car rushes by me visually, it rushes by on the screen, all the audio has it. Even before the car gets on the screen, I'm going to hear it approaching the screen. I'm going to see it moving, and then I'm going to hear it moving, and then I'm going to hear it after it's off screen. And all of that is laid out and computed to make you feel like the car just whizzed by me, right? There's kinds of masking that happen, and that is, it could be that there's a louder sound that makes it so I can't hear the other one. So you see this a lot when you're in a loud environment and somebody's trying to talk to you. Well, those two audio things are not going to work well together. So trying to talk in a loud environment. And then there could be physical objects that block the sound, right? So it could be something like this, where here my voice, the sound changes a lot when there's some sort of occluder in front of the source, right? And not a lot of systems actually do this sort of thing. We'll take these things into account when they're producing audio. So the types of display technology, we have head-worn technology, so earbuds. How many of you have used earbuds before? These things? Okay. Don't. It's like the worst thing you can do to your ears. Is to shove these things in your ear canals because you're just killing your hearing. So this is the worst thing you can possibly do, even though Apple wants you to buy them. You really just don't want to have these things. But anyway, you can use them if that's what you have. So these are in-ear. These are over the ear. These just kind of sit on your ear. They don't block out much of the real world, but they sit on the outside of your ears. These cover your ears, but they're open in the back, so there's actually air here. So the real world goes through. These are closed back, but still covering your ears. And these are what are called bone conduction headsets, and we'll talk about this in a minute. But there's a whole range of things that you can use for head-worn audio display. And really high-end audiophiles, some will swear these are the best cans you can get. These open back are just really, 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 really good. Anything else is just, you're just doing yourself a disservice. The physics of these are the best thing, and whatever. They could be right, could be wrong, doesn't really matter. But there are different things that are available, and they give you different benefits. These are really inexpensive. These are really inexpensive. These are getting more expensive, coming down in price. But once you get this set of cans, this is a really, really good set of cans, but it gets pretty expensive. And then bone conduction uses, instead of feeding the sound through the air, the sound is conducted through your cheekbones or through the mastoid bone behind your ear, this right here. And have you ever heard yourself speak, like a recording of yourself? And how does it sound? Different. How? Do you like it? Why don't you like it? Strange, right? It sounds very different than, wow, I really sound like that? It's like embarrassing, right? And the reason is when you talk, everything is vibrating in your head. And you're getting these low frequency vibrations that are shaking the cochlea, which is the spiral thing, in your ear, and that is giving you a lot of low frequency components. So when you hear your voice that's recorded, it's always higher. It doesn't sound as deep and rich as you think it should be. It always sounds a lot higher. And the reason is all of these low frequency things are just cut out when it's air conducted, because all you're hearing is what's coming from here. You're not hearing coming from here and coming from here. Okay? So this approach takes advantage of this bone conduction and says, all we're going to use is bone conduction. So you take these transducers, they're really just kind of speakers, and you put them on your cheekbones and you play audio through them. And they shake, so they shake your bones, which shakes your cochlea, which allows you to hear. Okay? Sounds really bizarre, but it's actually pretty interesting. And I forced myself to wear these for about a month. So when I was at work, I wore these every day in an open environment like this. And I'm like, wow, I was listening to music. The audio is terrible. It's just terrible. After a couple weeks, I'm like, actually, it's not so bad. And the good thing is I can hear people when they sneak up on me, So I hear like my boss shuffling up behind me, and I'd be like, quick, change the display to something important. And I could actually interact with my environment a lot better. And usually we wear these things to cut out the real world, right? I want to concentrate on my music and everything else. These are actually really good because they allow you to mix the real world into what you're doing. But you can still, they do provide some amount of split off. So you could also have some things mounted in the room. So you could have a stereo, like 2 speakers, or you could have a 5.1. So the 1, in this case, is usually the bass. There's also, in the 90s, there was this technology called a sound cube. And what it would be is you'd be sitting in your chair, and there would be 8 speakers, 2, 4, 6, 8. And all of the processing was done so that you could actually make a sound appear anywhere around you, because you would just mix the signals going out to these speakers, such that if if I was sitting here and you wanted the sound to come from here, then you'd make it so that these speakers contributed a lot more to the sound. Okay? So I didn't have to wear anything, but I had to stay inside this cube in a known location. So I wasn't very mobile in what I was doing. But they worked pretty well. And then we have different kinds of sounds. So this is, again, this is more a design part of the talk. So we have this technology, but typically in an experience, so in a game, because a lot of this is maybe around gaming, is you have the opening music, right? So, welcome to the game, and you're reading through here's the tutorial, here's a little backstory, blah, 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 and then you have the closing at the end. You could have area-based music, you're playing a game, you walk into a certain room, you open it up, and there's music playing that's the fire room music, right? Or the ice room music, whatever. So it could be that there's music that changes based on the location that you're in. There's music that changes based on what's going on. Do you have any examples of this? What's going on in the game? I use this a lot because I die a lot. So often when a bad guy shows up, the music will change to fight music. Dun, 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 and then you kill the last one, and then it's dun, 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 dun. So it's dun, 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 dun. You kill the last guy. Dun, dun, dun. So the function of the current thing, they want you to know, dude, there's someone bad around. Better go find them and kill them. And then you kill the last one. Immediately it changes to the walking around music, because that's the function. That's what's going on, right? So it's there for a reason. It's really there to alert you. And I'm sure all of you who've played these kinds of games have used that to your advantage. Like, I didn't see him, but I knew he was there because the music was telling me that he was there. You also have character-based music. Whenever this character's on the screen, you hear this sort of thing. And then kind of storyline music, maybe the music changes based on what's going on. You also have non-player character speech. So you have somebody talking to you, so these NPCs. Sometimes you hear yourself in games, like, boy, I wonder what's behind that door, right? You have these things talking to speech of different kinds. And then you have non-audio speech, things blowing up or pulling a lever and you hear something happen, right? This audio, that's so non-speech audio. Unfortunately, this doesn't play on this machine right now. So, but some examples that you have. The opening music can sometimes really set the stage for, is this a happy game? Is this kind of a serious game? And so you'll have the sound designers write a score that's really indicative of what to expect in the game. It could maybe forever be linked. So some of you have played Zelda or played some really epic games in the past. If that music ever came on the radio or you heard it somewhere, you'd be like, oh, it's great, I remember that from blah, blah, blah. There's now orchestras that will play video game music. They'll have special nights where they'll play all of the, video game music from Final Fantasy or something. This was a really great game in the 90s called, does anybody recognize? No, nobody. Yes, what is this one? Yeah, so this is Lemmings, which is a really great puzzle game. And anyway, they had this Pachelbel's canon. And it's like, da, na, na. Anyway, they had all of this music that was playing, and whenever it played, it just makes you think of this. Things that change in area-based, like things like you're in the country, or you're in the city, and you'll hear changes to the music there. I kind of already talked about this, so I'm not going to go too deeply. Somebody's attacking you, you should see these things. This was another sound clip. It was going to be ba 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 da ba ba da. Does anybody recognize that? So that's a big bad guy, half cyborg, right? So when Darth Vader comes on the screen, you heard Darth Vader's music. When Luke Skywalker's on the screen, you hear Luke's music, right? This is a very common thing that's done in movies, is that every character has their own theme music that's played whenever they come on screen, and there'll be a variation of it too, right? Many RPGs use this sort of thing too. And then again, you could have a recurring theme, so you could have a certain riff that's played, and it's changed in different parts of the game to give you kind of continuity. And sound is unbelievably important in terms of the user experience that you put together. And unfortunately, it's often an afterthought in a lot of, people really focus on the visuals and everything, and you really notice it when the sound is really treated as a first-class object in the game or in the experience design. It just makes a huge difference in the overall experience and people buying into it. Again, I'm going to pass on some of this. There is big money now, so a lot of in animated films you see this a lot, where there are big name actors actually doing the voiceover for different animated films. The same thing in games, they're hiring big names to do audio and some of the games, and sometimes it really makes a big difference. Non-speech audio has been a really beautiful thing to look at in film for a long period of time. So let me see if my audio is on, actually. We'll see. So this guy called Jack Foley came up, kind of was a pioneer in this, so now it's even called Foley artists, or this job in Hollywood where these people, if somebody, for example, there's a horror film and someone's arm gets broken, you don't want to actually break someone's arm to get that sound in the movie, so they'll take things like celery and they'll break celery. They'll record that, and the vision of someone's arm breaking and the sound of celery breaking together really makes you, oh God, I could almost feel the guy's arm breaking. And it's because, so what Foley did is he found all these things that had nothing to do with what the vision was actually showing, that sounded from a user experience point of view, really drove the point home of what was going on, right? And so so snapping celery mimics bones breaking and things like that. And a lot of these are exaggerated. So he would take two pairs of shoes and on a piece of wood with microphones, and he would go, so we'd actually have somebody walking around, and there would be a little sand on it, so when they turned, you hear this, the person turning. He had little doors that he would open and close, and he would watch the movie and record the audio as the movie was playing, and he would do all these things, and they would capture it and then make that the soundtrack for the movie. And it's really fascinating, but it's really hyper reality. It's much more exaggerated typically than what it is. It actually blew my mind the first time. It made me really sad when I realized that all of the audio that was done in movies wasn't done as they were shooting the visuals. It's all dubbed in later. And that was always it was really shocking to me, because it really was like, oh, they're just faking everything. Like, where's the reality now?
It's like the lasers in Star Wars are actually fence wires
Yeah,
that have been
yeah.
twanged.
Yep. So this non-speech audio can be used for a lot of different things, bumping into things, bushes, rustling, animals, really kind of anything that works can be used. So to Rory's example, Ben Burt, who is really one of the pioneers of this, this is him up in the hills north of San Francisco, and he would go anywhere to get any sound that he could get, and then mix them all together. So he went around, and there were these high tension wires, these big power things, and they were held up by these cables that had a lot of tension. So there were these steel cables going up, and he took his recording thing and he took a hammer with him and he just hit these cables, and it would go tong, 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 and he recorded all that stuff. And hopefully this will play. We'll see. Where's my cursor? Anything? So this sound is a TIE fighter flying through, and it really is an elephant going, roar, and a woman screaming. And he mixed all these things together to get that one sound of this TIE fighter flying. Right, and it's such an iconic sound now. So this is the Wookiee, which is Chewbacca, a walrus, and a bunch of animal sounds I'm doing. So again, he just created these sounds. It wasn't somebody going, they could have asked me, but I said no. So these laser blasts are literally So he's doing this, he did this a bunch of times, he recorded these clips, really modified them in a lot of ways. And then the lightsaber sound, he really took an old television that was tuned to no channel at all and just recorded it. So it's all just a bunch of static that he's put in at different pieces at different times. Right? So all these really are, I mean, to me this is just so cool that this is a job that you can go off and do. And this is all user experience design. This is all he's doing is trying to design these audio experiences. So the other thing is you often hear like the person breathing or their state, are they tired? You can synchronize these. It also confirms things that I've reloaded or the ping sound, a door has been unlocked somewhere. These can be used. So if we think about sound, the physics of sound is that, so most people think of sound as this kind of wave, right? So there's a frequency and an amplitude for the sound. Actually, sound is a pressure wave. It's actually a longitudinal wave. It's moving this way, not this way. We represent it this way graphically because we can plot the values. But what's actually happening when you make a sound is that the air is being, the frequency of the air, the pressure is being moved, and that moves my eardrum, and that allows me to hear. So it's these pressure waves that actually cause sound to happen. So it's these are coming in and they're bending my eardrum, and the frequency of these pulses, the frequency of this pressure change is what allows me to hear. So I have, let's say, a microphone. I can capture a sound wave, and then I can show the frequency of these pressure waves and the amplitude of how strong they are. And I can plot those in this way. But it's important to understand it really is a pressure wave, and this is why I'm allowed to hear. So it's a longitudinal wave. You can think of it that. So we do have these, at least two knobs that we can change with audio, which is the frequency, which is the distance between these peaks, so how frequent this happens. So this is a low frequency, so these peaks don't happen, the pressure doesn't happen as often. And I have high frequency waves. So when we talk about speakers that produce audio content, some speakers are optimized to produce higher frequencies and some for lower frequencies. And again, that's because that's the technology required. So the frequency determines the pitch of the sound. So the frequency, so that's a change in frequency, right? So the pitch has changed because the frequency has changed. And amplitude is the intensity. So I have to go, it's the same pitch, but the intensity has changed. Okay, so the amplitude has changed. So you can think of it as loudness, but loudness is a subjective thing. So I will have an amplitude, but you might hear it at a different loudness than you, right? Because this is kind of like this localization. So these are objective things. So I can objectively change the frequency and amplitude of an audio signal. Okay, and just like one of the interesting things about audio is that there's this inverse square law, which you see a lot in physics. And the idea here is that the intensity of the sound drops off with the distance from the source. So, and it's not linear. So in other words, it's 1 over the square of the distance. So that what that means is something that's really close to me will appear very loud. Something that's away will appear softer. And the change will follow this law of inverse square. So the further it goes away, it's going to drop off actually precipitously. Okay. So again, this is just kind of the technical bits. The processing that we can do. Audio is made up, again, very simply as a source and a sink, or a source and a listener. So I have audio that's produced and I have audio that's consumed. And you can say, well, if nobody's around, I'm still producing the audio, but there's nothing there to hear it. A microphone counts as a listener of some kind, right? So music is typically sourceless. There's some genres where they'll build in changes from left to right. There's stereophonic sound. There's quadraphonic sound that kind of fell off, and now there's ambisonic sound that's coming back now. But in general, music doesn't really come from anywhere unless there's like a radio on the table that the music should come from in the environment. And then sound, as it goes from a source to a listener, goes through a bunch of changes. So the reason this room is not good at what it does in terms of sound is because when it leaves my mouth, it's doing all sorts of bad things. It's bouncing a lot, so all these shiny surfaces make the sound bounce around a lot. Okay? So this is called reverberation. These panels absorb sound. So the idea is when I speak to this panel, the sound will get absorbed and it won't reverberate, which should make your experience better because you're not hearing this really this echo chamber effect. So you have some things that reflect, some things that absorb, and some things that occlude sound, right? So you have some occluders that will change the sound as it goes from the source to the listener. So if you think about this, does this sound familiar? Is this like anything else that we see? So light, when it's produced, bounces off objects, it's absorbed by objects, and it can be occluded by objects. Okay? So what a lot of people have done in the early days is to try and apply the same processing that we do for visuals, we apply to sound. So there's something called ray tracing. And what ray tracing does is it says, okay, I'm going to draw a line from my eye through one pixel on the screen and see what that would hit in the environment, and then I'm going to color the pixel that. So if you think about this, if I'm going to draw this scene, I would send a ray to over there, and it would be kind of whitish black because it's going to hit that part. If I shot it out here, it would be really black. And some things, if I shot a ray, it would bounce off of something because they're reflective surfaces, so they're shiny. And so I would see not that, but I would see what's reflected in there, right? And so I would bounce another ray. So this is called ray tracing, and this is used a lot in graphics to make really good pictures. And so we could think of audio the same way, and that I have a source and I have a listener. If I wanted to say that audio coming from there, what's it going to do when on its way here? Well, some of it is going to be bounced over there, some of it is going to go over there, some of it's going to go directly to me. And so what I can do is I can process this, I'm the listener, I'm here are my ears. This ear is going to get this information based on this room and that sound source. The frequencies and amplitudes are going to change, and then I can compute what each ear should hear from there. Very expensive. It's an extremely expensive thing because audio can bounce anywhere. So it's very, very hard to do in terms of computationally. So just like light, I have different materials. If this is a different material, I can actually take that into my calculation. I can treat the sound, and it's really, really expensive. So what we do is we just cheat. You say, you know what? That's great. I'm visually dominant. I'm just going to kind of punt. I'm going to make the audio be good enough, and then the experience will be good. So I could spend all of my processing power getting the audio to be exactly right, and then the visuals are, it doesn't really matter. So I can compare. If I got the visuals exactly right, and I got the audio exactly right, and I gave them the scene with these two things together, and then I made the audio non-spatialized, and it didn't change the user experience at all, like the questionnaires or their performance or whatever. I've spent all this time making this really great audio, and it just doesn't matter, right? So what we do is we make approximations, and we do this in graphics as well. But we make approximations. So we can say this room has a reverberation component. So this room has a reverberation component of 8. But the next room, it's a really nice room that's been set up very well. Its reverberation component is going to be at 3. So what I do is for every source, instead of tracing where it's going to bounce, I say, in general, I'm just going to apply reverberation at the 0.8 level for this room and the 0.3 level for that room, because there's no way I can computationally figure all this stuff out. But in general, this room will sound different than that room. So in the environment, when they're listening, they're talking, and they leave this room and they go in there, they will hear a difference. And that, combined with the visuals, should probably be enough. And I can measure that. I can make a user study where I can combine these two things in varying amounts with different computational, different delays, and I can design a user study my hypothesis would be better audio leads to better depth of presence. There's a hypothesis. I can design a user study around that and measure how true that is. And then I can make a contribution saying, it really doesn't matter. Just put audio in. As long as there's audio, so it did make a difference whether there was audio or no audio, but the kind of audio was really not that important. So don't worry about it, right? So there's lots of things we can look at. So we can get our sound sources by recording them. We can say, okay, I want to record this character, and I'm going to just record you, and you're going to say, stop, don't, come back. Right, okay. So I stole your purse, and I'm going to record the person saying, stop, don't, come back. Okay, great. Or I could somehow try and use a text-to-speech engine that I type in, stop, don't, come back, and it says, stop, don't, come back, right? And I can either generate it or I could capture it. And it's the same thing with textures and visuals. I can either take a picture of a brick wall or I can try and programmatically create a brick wall. And the same thing is true here. So I can get high quality sampled sounds using where Ben Burt has walked around and recorded a bunch of stuff, and they're cheap to capture. They're easy to get realism because they're recorded from a real thing. Like I can open and close a door, record that sound, and use that as my open and close door sound. And it's going to be very realistic because it actually is what it is. They're expensive, can be expensive to store. They could be very, very big files. They're difficult to manipulate. So if it's a door closing, but the door's made of wood versus metal, and I only have one door sound, I can't really change those really easily. So they're a little bit brittle in that way. Synthetic sounds, I can basically, since I know that all sounds are frequency and amplitude combinations, I can just sit there with a mixer and I can theoretically generate any sound that I want, because it's just sound signals. As long as I mix these things together, I should be able to generate the sound. It's very time consuming and not really intuitive. What happens when I change this? What does that do to the overall sound? So from sound design point of view, that's hard, but it can be really powerful. So there are these different things that I can do, and I've already shown you some. So these synthetic sounds are built up of different waveforms and different parameters of the waveforms, and I can combine them in different ways. And it often works for non-speech sound. So again, I have these two tones. These are just frequencies and amplitude. If I combine them together, like I take a sample here and a sample here, then I'm going to get this sample here. Right? So I have values and I can combine them, and this will give me a new sound. And all I've done is combine these together in some way. Okay? But it's really unclear what that sound is. Right? Is that a door? Is it a dog? I have no idea. Right? And you can combine these. I have these three tones. I can combine these together. I'm going to get this waveform here. Right? So these are the three overlaid on each other, these different colors. The black one is the resulting form. But it's very unintuitive to know what that actually sounds like. But sound designers who do this for a living can really tweak this stuff really interestingly. Okay.
You can usually pick up the bass frequencies easier than the others,
Yeah.
the lower frequencies.
Often, yeah.
Yeah.
So the other thing is we have these analog signals, right? These waveforms, but we live in a digital world these days. So often what I need to do is I need to take this signal and I need to digitize it. And the way I do that is by sampling at a given frequency. So I say, what was the value here? Okay, that's what it was. What was the value here? Okay, that's what it was. So I can go through and I can sample this. And if I just store these values, these discrete values, I can reproduce this waveform because I have enough information to do that. Okay? And if it's digital, it's much smaller. I can store it. I can play it back. I can manipulate it. So I have these two things. So this is a lower sampling rate. This is a higher sampling rate. So there's more samples per unit here than there are here. This is a higher sampling rate. So I have the same waveform, but I'm taking more samples per unit. Okay. Low bit rate means that I can either, so this, at any given point, the level that I can record is either here, 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 or here, here, or here. And I can't, for example, get this particular point because it's not at one of my bars. So this is like, think of this as an integer range, not a floating point range. So I need to say, well, is this particular point closer to this one or this one? And depending on that result, I'm going to choose that value for that. So that's the number of bits that I can use. And this is the number of samples that I take over time. Okay? And so these are important when you're recording audio, when you're trying to get audio, is what's the sampling rate and what's the bit rate. So that determines how well I can reproduce this actual thing. If I have this stored and I want to reproduce this signal, what it's actually going to reproduce is something that's like this, right? Because it actually doesn't know what the actual value was, it only knows what the sampled value. The sample told me it was here, whereas the actual value was here. But I didn't capture that. I captured this one because I didn't have enough resolution. Does that make sense? Maybe. Okay. So the types of shifts that I might want to do, naively what I might do is to just, when something is moving around, is I'm just going to change the delay between the right and left ear. So when something's over here and it's moving over there, I have a high delay to the left ear, still high but lower than the right ear, and now they're even, and then as it moves here, I'm going to have a higher delay in the right ear. So that's not going to get you this, but it will get you this. There's no notion of how far away it is in front or behind you, but it will give you kind of, it's moving through the middle of my head, right? Because that's what you're changing. So naively you can do that, and actually often this is all you need if it's combined with good audio, with good visuals. So it's very easy to produce. I have 2 speakers in my headphones, or I have 2 speakers on my desk. It doesn't really give true realism. There is no information about up, down, or forward and back. It just tells me where it is in relation to my ears along a line, because that's all I'm doing is I have 1 degree of freedom, and that is the delay between the ears, if that makes sense. So you can add more speakers to improve this. Yeah?
What about the headphones that have 5.1 or 6.1? Do you know?
Yeah, so they have multiple speakers inside, and I've never used them, so I haven't actually looked at them too much. So, let me just see how much more I have on audio, because I'm not going to get to haptics today, unfortunately. Okay, I know you guys need to run out. So Sangchul, what should I do? I have more to talk about, but not more time.
Up to you.
So how many slides do you read?
No, I still have a bunch of, I haven't done any haptics at all.
Okay.
And we have 1 minute left.
Then what about after 2 weeks later, then I have planned to give some presentation regarding evaluation in virtual reality.
So
maybe you can give
so maybe the third,
so minute or
yeah, that would be fine. Yeah, so this is really cool stuff, and I think it's important, but it's not directly, it's not going to hamper you from what you have to do for the, in terms of evaluation. So, but and so let me stop. But do you have questions about this? How many of you used audio before or know stuff about audio? Okay, so we definitely have some researchers in the lab. I just had a PhD student graduate who is really interested in kind of audio processing and audio use in virtual and augmented reality. And it is still a very rich field. There's still lots of computational problems in terms of, again, this notion of occlusion, dynamic environments. Almost nobody is working on kind of computing dynamic and really rich dynamic environments. A lot of the game engines have either plugins or have built-in support for spatialized audio, and more or less support for these types of processing of, if I have an object that moves in front of me, if I have a reflective object that's moving next to me, that should produce more reflection from the source to the listener, but does it matter if it's a shiny car driving by? And so it's, there's lots of things that could be done using audio from a technical point of view. And the main point for you guys to walk away with is really understanding that audio is very, very important to consider kind of as a first-class sense, not just visuals, and that there's lots of ways you can incorporate it. Okay? Good. Thank you. Did you stop?
Yeah.
Okay. Okay, so the red light's still on. I don't know why. It's